Da 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 da. Last screencast for the year. We did it. Good job, everybody. Happy Star Wars Day. May the 4th be with you. Here is your puzzler. Okay, and this last week we're going to be talking about Le Chatelier's principle again. This is the idea with equilibrium, that when a chemical system that is at equilibrium is disturbed by a stress, the system will respond in order to relieve the stress. So if you have an equation like this one, we have dinitrogen tetroxide and decomposing to form nitrogen dioxide. The two sides of the equation are not actually equal in the amount of the chemicals. An equilibrium is reached when the forward reaction is equal in rate to the reverse reaction. So as many molecules of N2O4 that are decomposing, 2 molecules of the NO2 are coming back together to form that N2O4. So it doesn't mean that we have equal amounts of the two chemicals. It just means that the rate of the forward reaction and the reverse reaction are the same. So in this reaction, if we add heat, more of the product is formed, the NO2 gas. So if we add heat, that is going to shift the equilibrium to the right. Conversely, if we remove heat by cooling the system down, that's going to shift the equilibrium to the left. So temporarily, when we add a stress, either the forward reaction goes faster or the reverse reaction goes faster until a new equilibrium is reached. So I have a brief video to show you on this.
We start this experiment with 3 tubes.
Sorry.
Containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
Okay, so this tube on the left here is in warm water, so it's shifted the equilibrium to the right. Okay, so let's take a look at another example. Oh, sorry, this same one. Okay, so this reaction is it exothermic or endothermic? If you said endothermic, you are correct. So heat is a product in this reaction. Okay, so endothermic reactions will shift to the right when temperature is increased. Exothermic reactions will shift to the left when temperature is increased. Now, not all reactions can undergo can reach an equilibrium. So if we think of something like combustion, where you're burning a candle, that's not a situation where equilibrium will be reached. Okay, all right, so if we look at pressure, we have a bunch of gases in equilibrium. You can see that there are more moles on the left side than the right side. So if we add pressure to the system is going to shift to the side with fewer moles. Okay, so like this gas is going to take up less space on the right side because there's only 2 moles of the gas versus 4 on the other side. Okay, so if we add pressure, it's going to shift the equilibrium to the right because there are fewer moles of gas on the right. So the converse is also correct. So if we increase the volume, equilibrium shifts the other way. Okay, now if we change the concentration of one of the chemicals, that will again shift the equilibrium. So in the first example, if we add more of the hydrogen ions to the solution, right, we have more of this stuff on the right, it's going to shift the equilibrium to the left. Okay. If we react the acid with a base, such as NaOH, so if we put some base in there, it's going to react with the hydrogen ion. That means that this hydrogen is going to decrease, so the nitrous acid on the left is going to shift to the right. So more of that nitrous acid is going to split up to form these two ions. Okay, now this has an application for the environment. We've talked about ocean acidification before, that the increase in atmospheric CO2, it's going to push all of these reactions involving ocean chemistry forward. Okay, so let's look at each one of these. So we have the carbon dioxide is increasing in the atmosphere, which means that the equilibrium in this first reaction is going to shift to the right. That means more of this carbonic acid is forming. If you recall from last week, some of you looked at the pH of sodas. The fact that sodas are carbonated causes the pH to decrease, which is why they're so bad for your teeth. Okay, now that carbonic acid pretty much immediately splits up to form these two ions, hydrogen and hydrogen carbonate. So that gets shifted forward. Okay, now because of the increase, this increase in the hydrogen carbonate also causes the carbonate ions that are floating in the water already to combine with the hydrogen to push the reaction further to make even more of this hydrogen carbonate ion. And that just has to do with the chemistry of this reaction. Even though we're producing more of this hydrogen carbonate ion, even more is going to be added to solution. Okay, and then where do these carbonate ions come from? Well, they come from seashells and from the shells of other ocean creatures, which you'll read about and learn about in the next piece of this. But calcium carbonate is part of the shells of a lot of different sea creatures. And when we increase the atmospheric CO2, which decreases the pH, that causes those shells to dissolve. Okay, so this has huge ramifications for ocean life. So I'd like you to watch some videos and read some articles about how ocean acidification is affecting marine life. Then you're going to read about just generally the power of water. So this is kind of moving away from ocean acidification, just how water interacts with the surface of the earth. Okay, and finally you're going to be watching and meditating to these one of these meditations offered by the Monterey Bay Aquarium. They're really lovely. You could pick one of the 6 to meditate to, and I hope that that gives you some calming experience and just hopefully an appreciation for the ocean. Okay, here's the answer to the puzzler. And thank you for doing a good job this semester. I hope to see all of you in the fall. Good luck with your final week of chemistry and your other classes.